Okay, this, like I mentioned before, you don't need to do your assignment like this. It's just another option. And it's a way to use Simulink that you won't see labs, because the labs are typically dealing with transfer functions and whatnot. This is operating directly in the time domain. So we boot up Simulink, and let's make this a little bit bigger. What I'm going to do is I'm going to build the second equation, and then I'm going to open up a model that I built earlier for this particular problem. So, on the right-hand side of the equation, we have the sum of three terms. You've got f, you've got k2y2, and you've got k2y1. So I'm going to need a summing block in here somewhere. Let's hope it's not super slow.
It looks like it's super slow.
Yeah. Okay, so we got a summing block, and just to make it look a little bit neater, I'm going to make it rectangular, and my summing block has the addition of f, and we're subtracting the restoring forces from the spring. So I need a minus and a minus in here. Make this a little bit bigger. I'm also dividing by that m2 term, so I'm just going to put in a constant gain. Oh, it's really, really slow. Okay, so I'm going to put in a gain. Basically, after I sum in every one of those signals that's in the numerator of the y2 function, I'm going to need to divide through by the mass. So here I'm going to put a multiplication by 1 on m2. Now I'm leaving it as a variable because in my MATLAB script I'm going to set the parameters, set all these variables in the script, and then execute Simulink. This is a bit more robust if you want to look at changes in parameters like you guys will need to do, because you're looking at variable spring stiffness, variable damping. So it's handy not to hard code these into your Simulink model. So let's just connect these up. So once I've added everything and I've divided it by the mass, what's coming out of this block here should be y2 double dot. So if I want to get y2 dot, I'll need to integrate it. We'll put an integrator block. This will make a little bit more sense after I build everything. And I'll need another integrator block as well to get y2. And then I'm going to want to save my data. So, oops. I'm going to want to save my data. So I'm going to put a 2 workspace block. And remember, 2 workspace, it's handy to change this to structure with time, because then you have the whole signal and you also have the actual values of the signal. So let's send that to the workspace. Now this isn't anywhere near complete yet. So in that equation, I have the terms k2y2 and k2y1. So if I want to feed those in, I can get this gain, put it here, just flip it around. So I need to subtract k2y2 over here somewhere. So I'm going to pick off the y2 signal, feed it into a gain block with gain k2, and then I'm going to connect it to one of the ports that has a subtraction. I'm also going to need an external forcing function. So for that, I'm just going to be very simple and just use a unit step. Now I might at some stage want to scale this step. So that's a unit step, it's just one. I could scale it by adding in a gain before it gets fed in. So I'm going to add this just in case this is another parameter that you will be able to set in your script. I'm going to call it famp, just amplify the force. So if I feed the step into the gain and then connect the gain here, I've got 2 of the terms in that equation. So I've got my f being added in, I've got my k2, y2 being subtracted. I'll need k2 times y1 in here as well, but that will come from the second mass. We'll need to repeat this for the first equation, and then link the coupling terms. I'm not going to do that here. If you want to see tutorials on how to build these things in Simulink, how to model differential equations, there's a whole heap of them up on YouTube. So I'm just kind of going through this quite quickly. We repeat the same process for the y1 equation, and what you should end up with is something that looks like this. Okay, so I've got the y2 equation up the top, the y1 equation down here. You can see dividing by the mass, integrate. K2, y2 feeds into here. Also got a K, where is it? That might be the wrong symbol, that should be a negative there, but I've got K2 times y1 also being added in there, and by forcing function. So this whole thing here models that second equation. Similarly, this thing models the first equation. Okay, so you built the differential equations in Simulink using the different blocks. Has anyone used Simulink like this before?
No.
No? Okay, this is what it was actually made for. Anyway, this is one way to approach it. Like I said, you're probably not going to understand just by me doing it here, but there are heaps of tutorials up online. If you're interested in solving your assignment this way, just go look them up. After you do it a couple of times, it becomes really straightforward. Okay, so you build your differential equations in there. Then we can go over to MATLAB, and I'm going to open up a script. Okay, so I mentioned before that the reason why you leave variables in your Simulink model is so that you can set them in your workspace. This is really handy for you guys because you need to loop through the different spring stiffness and damping values. So I set them all up here. The variable names have to be the same variables that you use in your Simulink model, obviously. I've mentioned this f-amp, which just amplifies the force. You don't need it, you can set it to 1, but it's handy in case you want to look at different scales of force. Simulink it's solving ODEs in a time domain. You're integrating signals, so you need some initial conditions. We had 4 integrators in the block in our Simulink model. 1 to integrate, well, 2 to integrate y2, 2 to integrate y1. So I need to set some initial conditions for the integration. Just set them all to 0. That's fine. Number of points here, that's just how many simulation points you want. DT, you want to tell Simulink by default will use a variable time step solver. And if it can predict what's going to happen next, it'll start using really big time steps. That's not good for actually resolving your response because you'll end up with little jagged signals. Set this time step to something small, 10 to the minus 3, this stuff runs really quickly. Set it to something small so you can get nice resolution of your signals. Stop sim, this is just the end time of your simulation. So go down a little bit. Then we get to actually running our simulation. We can use this simset command to set up options for Simulink. The initial state will give it the initial conditions. Just leave them at 0 for your purposes, that's fine. And max step will set up that maximum time step so that it doesn't exceed that. Sim command, this is what actually runs Simulink from your workspace. So this command is going to run the model example. It's going to run it for the period of time stop sim, and it's going to use the options specified up here. Okay, so you can execute that. I'll just run it. And what comes out of it is something that looks like this. Okay, so what I'm actually plotting are the displacements of both the masses. You can see there's a legend over there, mass 1, mass 2. You see these funny responses because you have two interconnected systems of different spring stiffnesses, so different natural frequencies. The two frequencies are of similar order but not the same, which is why you get the response of one superimposed on the response of the other. That's not really that important, but what I want you to concentrate on is the way that my plot looks. You see I've got very thick lines, they're easy to see. I have labels on both axes, you probably can't see the bottom one, but I've got labels, and I have units in my labels. I've got a nice big font. It's actually not that big for this classroom, but I've set up this variable here, font size, and I can make it larger. Let's go 24. Okay, it's a little bit easier to see now. And I also have a legend. This is the kind of plot that I'd expect in your reports. And I am really anal when it comes to plots. So if you give me a shitty plot, I'm going to penalize you severely. Like 50%. Mainly because I am showing you this now, and I'm showing you this script, which does pretty plots for you. Okay, so you might want to... Someone asked in yesterday's shoot, can I send this stuff to you guys? I asked Ian, he hasn't gone back to me yet. I probably can't. Send you the Simulink model at least, but something like this, feel free to take photos because it's just general MATLAB stuff. So yeah, plotting commands. Remember we've got structures, so these extract the structure's time and the actual signal. Set the colors and the type of lines that you use. Set the line width, make your lines thicker. I want a grid in there. You might want to play with your X limits. If it's going off to infinity, I don't want to see a signal going to infinity. I want to see just where the important stuff is. Label your axes. Change the font size so that it's readable. You might want to change the type of font that you use as well. These two lines here, this one's not that important. That just gives a fancier grid with different, it's kind of lighter in the background. So that's not that important. This one is though. This one changes the font size of your actual axis. So where you have 0, 5, 10, 15, whatever, this will change it to the same font size as what you've got in your labels. And then if you're plotting more than one plot on a graph, I want to see a legend. And the legend should not obscure any of your data. So you can use this location to move it around your plot window. Also, don't include screenshots of your plots. I don't want to see that grey, ugly grey background. Save your images as PNGs or EPSs or something, and then embed them in your documents. Okay? Okay. Any questions on any of this? Yeah.
You was just saying like last week you're gonna show us some kind of report style you wanna actually see.
This is a little bit of it.
Oh, okay.
Mainly the plotting stuff.
Yeah.
Is critical. Next week, we're gonna run out of time this week, so next week I can go through that.
Oh, cool.
But just for general setup.
Yeah, cool.
What else? Yeah, so let me stress, this has nothing to do with the lab that you're doing today. Absolutely nothing. This is just general using Simulink to do vibration problems, systems problems, analyzing a vibrating system. So yeah, feel free to, especially the plotting code, take note of that. Running Simulink from MATLAB, these commands, it can be a little bit tedious trying to figure them out on your own. It took me a little while, so maybe want to note those. There are other options that you can set. You can, everything that you change in the Simulink model, you can set through the workspace, but it's handy to build it first so you can see what's going on, and then just set a couple of parameters. But yeah, any questions?
Can you scroll up to the setup stuff again?
Yep. So the top bit here is, of course, this is all problem dependent. It depends on what parameters you actually include in your model. Make sure you include every parameter that appears in your Simulink model has to be specified here, otherwise it'll give you an error.
Is there a way to, if you're looping through array variables and stuff, is there a way to store each set of data?
Yeah, definitely. So you can just store them as you can extract, say, the arrays of your like whiteout signal,
Right, and then just put it
and then just put it in a matrix that's indexed. So it'll come as a row vector. So just, you know, y I all is equal to whatever it was in this image. Sometimes the vectors won't be the same length, so you might need to use a cells instead of matrices. All right, so that took a little bit longer than expected. Try to get started on your lab